Okay, Lab 2 is solution making, LLSA, and autoclave validation. Okay, so first part is solution making. Your lecture will be talking about how you make different solutions. There are different types of solution making methods out there. Of course, the first easiest method will be what? Define the weight of a chemical per given volume. So weight per total volume of your solution. Another way of describing solution making would be what? Molar solution. 1 molar, half molar, 2 molar solutions. So it depends on the molecular weight of each compound. You will dissolve that chemical into a certain solvent, water or whatever else. And another way of making solution is a percent solution. So in 100 ml volume, how much of the chemical will be there? That's a percentage solution. And then another solution making method will be, what if you have a stock solution that is concentrated already available, made by someone else? How you make a dilution out of that? For that, that CIVI equals CFVF. That equation is very handy when you deal with the dilution making process. Anyway, you should be familiar with the solution making math calculation. It's a simple math. You don't have to be afraid of that math part. It's easy once you figure it out. Practice a few times, and then based on understanding, you will do a hands-on practice through this lab. So you will be asked to make either 10x TE buffer solution or 10x TAE buffer solution, and once you make these solutions, you'll be using them when you do your DNA isolation or electrophoresis. Okay, and each buffer requires about 2 different chemical compounds or maybe 3 different compounds. Okay, by measuring out each compound and then mixing them up with the solvent. In this case, it'll be water. Okay, you will make each solution. So if you decide to make 10x TE buffer is made up with TrisCl. So trisma base, that's pH adjusted with HCl, is what TrisCl is. That's pH adjusted to about 7.6, about neutral. So 100 ml of TrisCl combined with 10 millimole. 100 millimole of TrisCl is combined with 10 millimole of EDTA. EDTA, again, pH is adjusted to 8. That is the TE buffer. Okay, the combination of those two will give you a 10x TE buffer. Normally, the working concentration of TE is 1x, so you'll have to dilute it 1 to 10-fold before you use it. So TE is a buffer that is commonly used in dissolving DNA. And then TAE is a DNA aggregate electrophoresis buffer you'll be using later on. If you're making a 10x concentrated stock, it requires 400 millimolar tris, same tris base, and then 0.2 molar acetic acid. So by combining tris base with 0.2 molar acetic acid, you will adjust the pH of the tris to kind of neutral pH range. Okay, that's why you add acid there. And then 10 millimolar EDTA. So they're kind of similar if you look at it. I mean, that's the hydrochloric acid is used there. Instead, you are using what? Acetic acid there. So that's the only difference. If you combine these 3 compounds together, you will get to make 10x TAE buffer. So I want you to do your calculation, math calculation, and based on your calculation, you find out how much of each component you would need, and by mixing them up, you will make a solution. That is your first task. So solution making practice. When you make a solution, you need to follow these steps. Number 1 step, find the formula weight of a solute if you're making a smaller solution, right? And then determine the molarity required and determine the volume required and do a little math to find out how much of your chemical you would need and how much volume of the solution you need. And then you're going to mix them up together. By doing so, you're going to dissolve the chemical into the solution. Okay, but when you do that, you start out with a less volume of the solvent, because when they're mixed up together, there will be a volume increase. To consider that, you always start out with the less volume than the final volume, right? And then if it's needed, of course, you need to adjust the pH by adding acid or base, depends on the pH value. Okay, once that's done, then you will check the final volume. So that's the last step always. Check the final volume to make sure you have the right concentration. And when you do the volume check, of course, always understand how you deal with the meniscus level, right? Once your solution is made, of course, you need to store your solution in a right container. It could be a Pyrex bottle of some kind. Once you put it in a container, you have to label the container with appropriate label. Your label should have all the essential information, such as what it is, okay, the name of the solution, concentration, date when you made it, and who made it, your initial. Okay, so those will be the essential information. So put a tape on your bottle with this information written on it. That's how you make a solution. So that will be your first exercise you need to carry out. And then the second exercise, which will take a long time. It may take about 1 hour incubation, and then before that you will have to mix up a bunch of different things. So about 1.5 or 2 hours will take for you to complete this second exercise. So it'll be wise for you to start out with this exercise first, and during the incubation time you can get to do the other exercise. Okay, so the second exercise is about the water that you will be using in the lab or using during your manufacturing. Okay, so if you are working in a pharmaceutical industry, okay, water is really important because you will use so much water during your manufacturing. So upstream process, you will grow your cells in some kind of growth medium, and growth medium's base is water, of course, right? And the downstream process, again, you will have to use bunch of different solutions, buffer solution or binding solutions or washing solution or elution solutions. So water will be used everywhere. So then what kind of water can you use? You're not going to use city tap water. Instead, you will have to use a very high quality water. In the pharmaceutical industry, the requirement for the water is determined by the U.S. Pharmacopoeia, and they call that particular water quality as water for injection. So the water is so pure, it can be injected into human body, there will be no problem. Okay, so then what kind of purity is that? So according to U.S. Pharmacopoeia or EP, European Pharmacopoeia, your water should be so pure, it will have very minimum amount of contaminants or any foreign substances. Inorganic content, any inorganic material, there should be very little bit of that. So when you use a conductivity to measure the conductivity of your water, that will be very low. So 1.3 microsiemens per centimeter. That is a very low reading. And then organic content, any organic compounds that can be present in your water, again, that should be very little. Less than 0.5 milligram per every liter of your water. Okay, and then another important thing, microbial content, any living cells that can be found from water. Of course, that's not allowed. So you'll have very little amount of living cells present there. Total bacterial count, it'll be less than 10 cells. So a colony forming unit is basically number of cells. Less than 10 cells will be allowed for every 100 milliliter. That's very little. And then another important thing is the pyrogen contact. Pyrogens are what? Kind of endotoxins. Those are broken cell wall debris of gram-negative bacterial cells. Why is that important? Because those broken debris of gram-negative bacterial cells, if they are injected into human body, they will cause sepsis. Sepsis is a very dangerous medical condition where people can die with a high fever. So pyrogen content matters in your drug, injectable drugs, because your drug will have a lot of water in them. So you will have very little amount of pyrogen or endotoxin in there. How much little? It's less than 0.25 endotoxin unit per every ml of water. So you need to measure all these contents and check if your water meets these standards or not. Okay. So out of those different tests, you will perform the pyrogen assay, which is called LAL assay. So endotoxin assay, that's what it will do, this lab. Okay. So again, pyrogens are fever-inducing entities made from gram-negative bacterial cell wall, broken cell wall debris. Those are what pyrogens and endotoxins. Okay. So when these bacterial cells die, and their cell wall debris maybe come out, and those debris will go into human body and they will activate the immune system, activate the immune system, and through that activation you will have high fever and you will have problem with that fever, and a lot of people may die from it. Okay, so exercise 2 is LAL gel clot assay. So LAL stands for limulus amebocyte lysate. So limulus amebocyte is the horseshoe's blood cells. That's what limulus amebocytes are. So if I show you, these guys are the horseshoe crabs. Horseshoe crabs, crustacean, living in the ocean bottom. Okay, they have special blood cells. Their bloods are kind of blue color, and then their blood cell lysates are what LALs are. Limulus amebocyte. Okay, they're lysate. Those are LAL. So those special proteins, compounds that are isolated from those horseshoe crabs, they are used because they have reactivity with the endotoxin. Okay, if there is endotoxin present, and these lysate proteins will bind and they will coagulate, meaning what? They will form a network. So they will develop some kind of agarose kind of a gel-shaped material. So that's what LAL would do with the presence of endotoxin. Okay, so LAL assay, there are a couple of different ways of doing it. Okay, the assay you're going to do is based on the gel clad assay. So if you add LAL with the endotoxin, it'll form a gel. So gel cloud will be formed. Okay, so but basically observing if you see a gel cloud or not, you can determine the presence or absence of endotoxin. That's the qualitative assay you're going to do today. And then there's another way of doing more sensitive assay that's considered as a quantitative assay. So some LAL could be conjugated with color substances, we call the chromogenic substances. And if those bind with the endotoxin, and they will develop color. So, and those color detection could be done using a spectrophotometry, right? So you can do a more sensitive, more accurate measurement if you have that device, spectrophotometry, as well as you have the chromogenic substance conjugated LAL reagents. Okay, so when you do a QC LAL assay at the companies, normally they do this chromogenic substance based assay that are more accurate. Okay. So how are you going to do your assay? So this is how you're going to do. There are two parts of this assay. The first part is detecting the sensitivity of your assay using the endotoxin standards. So what do I mean? So you will develop a series of conditions where different amount of endotoxin is present. So maybe first tube with no endotoxin, the second tube with maybe more endotoxin, next tube less endotoxin. You'll create a serial dilution of the endotoxin, and you're going to add LAL to those tubes and see at what concentration of LAL you can form the gel cladding. Okay, so the first part is done to develop the gel clad formation in your test tube. So this is how the assay will set up. So if you have maybe 5 or 6 tubes there, okay, in those tubes, maybe the first one would not have any endotoxin added. That's going to be just pure endotoxin-free water in a very clean test tube that's guaranteed to have no endotoxin there. It's an endotoxin-free tube. Okay, that's going to be your negative control. So to that, you're going to add LAL solution to see if there's any clot formation or not. Of course, since there's no endotoxin, you're not going to have any clot formation there. That's a negative control. But these tubes will be given with different amount of endotoxin. For example, you are given with the endotoxin stock solution. Okay, from the stock solution, you will dilute that stock solution to 1:1. Okay, so let's say your stock solution has a 1 endotoxin unit per ml. Okay, that'll be diluted down to maybe a half endotoxin unit per ml by mixing the same volume of that endotoxin with the same volume of endotoxin-free water. Okay, once you do that, mix them up, and then transfer half of the solution to the next tube that has the same volume of the endotoxin-free water. Mix them up. Okay, and you transfer that to the next tube that has, again, endotoxin-free water. Okay, mix them up, transfer half of that to the next tube that has endotoxin-free water. By doing so, you are creating a serial dilution. Okay, so that's one endotoxin unit per ml, and then you have what? A half endotoxin unit per ml, and you're going to have a quarter endotoxin unit per ml, and you're going to have 1/8 of endotoxin unit per ml. So you're going to go down the endotoxin concentration by making these dilutions. Okay, so you have these series of tubes that have smaller amount of endotoxin continuously. And once you create those tubes, then you're going to add LAL to all those tubes together and see which of the tubes will form the gel. Okay,